All right, moving on. I heard a cuss word. That's not
did
cool.
too.
That's not cool on the
Steve
video.
Jobs.
Nitro -5.
Nitro -5.
Nitro wouldn't say that. All right.
Do you know this
Steve
kid?
Jobs. He's
I
such
deny
a
that.
weasel.
All right, moving on. Let's move on quick. Come on, guys.
ran.
Hey, if we don't get back on task, I can't tell you my story, and it's a really, really good story, isn't it, Brooks?
I told the story about
It's an awesome story.
Brooks looks really excited.
He is so excited that he's here for a second time.
He's so excited.
All right, now, we really need to move on here. We can also talk about reactions and the loss of mass and how mass can be converted to energy. What's that good old fancy schmancy equation for mass converting to energy? E equals mc squared. So what we're going to do is look at a reaction like this, and I'm just for time's sake, they went ahead and got the masses of all these different nuclei or atoms, and I'm just going to write them here. And again, these people are kind of wacky, and I'll show you why in a minute. But this thing actually weighs 225.9971. The radon weighs 221.9703, and the helium 4.00150. If you were to do the math, you would see that the sum of those two things is way less than less than 225.991. What happened to the mass? The mass was released as energy of some sort. Well, not released. The mass was converted to energy, and that was released. So you're going to need to be able to calculate how much mass, we call that the mass defect, and then how much energy was actually given off at that point. Here's why these people are crazy. Look at this. What's wrong with negative 0.0053 grams?
Negative mass.
No, negative mass. They're putting the negative because that's how much is lost, so I'm okay with that.
Oh, it's in grams?
Grams? Is that how many grams was lost? Are these grams?
No.
No?
They're atomic mass units.
They're grams per mole, exactly. These are grams per mole, all right? So we ultimately have grams per mole here, so our final kilojoules is in grams per mole. Kilojoules per mole. So one thing that I want to point out, when you are using the theory of relativity, you have got to convert your mass to kilograms. Can anybody tell me why?
Physics.
Joule, I heard that, because that's how joules are measured. What is that? Tell me the units on a joule. Somebody. Y'all are in physics. If I go tell on you, Mr. Sage is going to beat you guys with a stick.
Kilogram, meters,
With a meter stick, exactly. What? Kilogram times, it's in Newton meter, so come on.
Meter squared per second squared.
Meter squared, second squared. There we go. That is a joule. So we cannot put in our mass defect as grams. We have to put it in as kilograms, or kilograms per mole, whichever. But if we put in kilograms per mole, our final answer will be in a unit of energy per mole. So that's a big thing to watch out for. The last thing we're going to talk about is binding energy. What's binding energy? Okay, one at a time. Who wants to talk? Avi, loud.
The energy required when you put the two things together.
What
the
things?
Atoms.
Okay, actually we're looking at the binding energy of a nucleus.
So it's just how much energy it takes to hold the nucleus together.
Okay, why does the nucleus need to be held together?
Because all protons are positively charged, so naturally they're repelling each other.
Correct. All protons are positively charged, so the inclinations for those things to repel. Something's holding them together, so that's what the binding energy does. Some of the protons and neutrons' mass is converted to energy, and it's the glue of the nucleus. Okay. You're going to be using the mass of the protons and neutrons to do that. Do not memorize that. I will give that to you, and we're going to work a problem with that here in a minute. Nuclear fission, that's what y'all love. Atomic bombs, all that.
Is that grams?
See, oh, this is what I'm saying. That's what the crazy people again.
Oh,
Yeah.
okay, moles, yeah.
It's grams per mole or AMUs, atomic mass units. So yeah, absolutely nutso. That's why you got to be careful. Just because something's in print doesn't mean it's right. And whoever did this, they're not real bright. And I'm just too lazy to like recreate a handout. I'd much rather make fun of people in the process. All right, nuclear fission up here. All you need to know is that that's what's going on in all the bombs that y'all love to talk about blowing up. In all your nuclear reactors, we're dealing with energy produced as a byproduct of fission. Fusion is what goes on in the sun. Fusion Cold fusion would be awesome. We're actually going to watch a movie after the AP exam called The Saint. Val Kilmer is like about to find the key to cold fusion with Elizabeth Shue, who's like this really cool doctor who has a bad heart. It's awesome. So
Like
we're
a
going to be
soap
watching that
opera?
after the AP. What?
Is it like a soap opera?
No, it's a movie. It's an awesome movie. And Val Kilmer, I'll just tell you, he saves the day. The world doesn't
You ruined the
explode.
movie.
Yeah, we ruined it.
Wasn't,
I know.
wasn't there a study recently that was like if we had kept up like the Cold War era like funding for nuclear projects, we would have like fusion by now.
Yeah, and that's funny because the movie is based off the Cold War. So based on the movie alone, yes, you're absolutely right. Because I get all my historical facts from Hollywood.
Yeah.
That's how I run my life. So yeah, you're right. I think so because the type of research they had going on was leading in that direction. Okay, so for fusion, all you guys need to know is what happens on the sun. I want you to know that you're mixing 2 deuterium, which is just heavy hydrogen. Deut-2, heavy hydrogen. Two neutron hydrogen. Hydrogens come together and make a helium atom plus a whole lot of energy. All right. So that's all you're going to need on the AP. They don't get deep into any of that stuff. Okay, so let's practice, practice, practice. Because practice makes perfect. We're going to do a few from each of these pages. See how well you do. Alpha emission. So antimony is what? You tell me, because turns out I know it. SB, thank you. So we put 121. What's the atomic number of antimony?
51.
I have my notes all filled in, so. Alright. Alright, we're going to have alpha emission. So what is alpha emission? 4 over 2 HE. Or you can put Jesus fish, I don't care which one. And in order to add to 121, what do we have to add? 111 over 117, excuse me, math is hard, over 49, and we get Indian.
Yay!
Go India!
Please don't start imitating your parents again.
Welcome to India, where the cows eat hay and we drive auto rickshaws every day.
Okay. As an employee at Westlake High School, I have to stop you from further insulting your fellow Indians.
Insulting? You don't have Indian accent, you all have American accent.
All right, moving on. I'm sorry for those of you at home. I apologize. 238 over 92 is our uranium. And if we have uranium, y'all have got me so shaken up right now with the whole thing. I don't know how to handle this. We're absorbing a proton. So what's a proton?
0 over 1.
How about 1 over 1? And then it's absorbing, so it's going to be on the left side as opposed to the decay or emission. And then we end up with 239 over 93 NP. This is different than a beta particle. Okay, beta positive, a positron. Oh, I did say a positron was the same as a proton, didn't I? Yeah, I lied to you. How about that? A positron is like an anti-electron, but it's not the same as a proton. A proton is 1 over 1p, so make note of that.
Electron does not have.
Dude, 239.
Right, it's an anti-electron.
No problem.
We're good.
All right, so we have neptunium here. Let's keep going. We've got aluminum, 27 over 13 aluminum, and it's alpha emission again, so 4 over 2. I'm going to do HE, I'm more comfortable with that. And we make 23 over 11. What is that one? Sodium. Okay, sulfur is a really, really, really common radioactive isotope used in medicine. Also used in scientific research for plants. Sulfur and phosphorus, lots and lots of use. That's beta emission, and we make 32 over 17 what?
Whatever comes after chlorine.
Chlorine. Okay. And then positron. Positron emission, that was where I lied. Positron is the anti-beta, so 0 over positive 1 beta. And what are we going to get? One of the Jackson 5? 72 over 32. It's germanium. Germain, Miss Linda. Jackson 5. Y'all probably didn't know that.
No.
No, we did. Or I did.
Did you really?
Michael Jackson. Courtney, stop on.
Courtney would,
Yes,
yeah.
Michael Jackson, correct. Okay. All right. If you want to check yourself here, this is a check your own, test yourself. Am I still on the screen?
Yeah.
Test yourself here. What you can do, you can make uranium undergo all of those different emissions, and you need to make sure you get polonium-218. So you can do that on your own if you need to practice it. So let's practice a typical math problem. So hopefully you have your calculators fired up.
Boom. Sorry,
She's got this. All right. Polonium-210 decays by the emission of alpha particles. Its half-life is 138 days. So the first thing we want to do, it says write out the decay reaction. So we have 210. What's the the atomic number of polonium?
84.
84. We're going to go undergo alpha emission, and we're going to get
Lead.
206 over 82 lead. Okay, first says calculate the rate constant. How do I do that? What do I use? T1/2 is 0.693 over K. And so we plug in our half-life of 138 days. And tell me if I'm wrong, I got 0.00502 days to the minus 1.
Ah, we can't see it.
Oh my God!
Ah.
Courtney,
Okay.
calm down.
All right.
She
I'm
watches
sorry.
this, she's sleeping.
Okay, shh. She will be watching.
I know, that's what I said.
Hi, Courtney.
So why are
Shout
you
out to
continuing to
Courtney.
talk about her? Stop.
We miss her. We miss her. I miss you, Courtney.
I miss you flicking me and stuff.
Come home.
I'm just trying to replace you.
South Africa.
Okay, would someone mind telling me if that's right? Is
I
that
love
something?
Courtney.
Yes.
That is right.
Yeah.
It's
Okay. Lee, what are you doing with your phone?
sorry.
Yeah. All right. How long will it take before? Yeah, he tried to make me think he was using his calculator, but
I was just
I'm smart.
playing
See, I know what an iPhone looks like, and I know what a smartphone
Hey,
looks
good thing I don't
like.
have one.
It's not my phone.
Well, it wasn't a calculator. Yeah. So funny today at the attendance office, here I'm going off topic, there's a girl who she was late, it was in the first period, about 15 minutes, she was walking toward the attendance office, and right before she got there, she took her Honeyham cup of ice and Dr. Pepper or whatever, puts it down on the ground, and is about to walk to the attendance office, and she looks at me and I'm like, so? And she was saying, well, I just wanted to put it there, I can't turn it, basically she didn't want them to see she was at Honeyham, because it would probably contradict with her lie. So, my point is, we're not that stupid. How long will it take before only 5% remains? We start with 100%, we end up with 5, let's treat that as grams. Shh, ln of 5 minus Arnav and Arun. I'm going to send you to another country. Again, stop. Equals negative K, 0.00502 per days. And then T is the time it takes, because that's what we're looking for, how long. So what did y'all get?
596.7.
So 597, what's the unit of time? Days.
Wait,
Is that a
number
lowercase
B?
k?
Wouldn't you have to convert days to years?
Why?
Well, because I thought you said the units for K were years.
No. In the particular problem, we were
Oh.
given the half-life in years. You can use whatever unit of time you want,
Okay.
as long as you're consistent through it, okay? Because remember all the problems we used to do were per second, right?
Yeah.
In kinetics, it can be whatever.
Okay.
And seconds just wouldn't be very realistic in these large half-lives. The numbers would be huge. Okay, one thing I want to take a side note on, if I ever give you data, and it's concentration and time data, and I really meant that to be X and that to be Y. Say I gave you all this data, and I told you to find K for me. What would y'all do? Okay, Raleigh's got it. Graphing. How would we graph this since it's first order?
The L